2, 1.
2, 1. And also, if I evaluate this gradient vector and my base point 2 minus 2, I'm getting a vector equal to 8 and minus 4. Yes?
8, 4.
8, 4, I'm sorry, 8 and 4. So I have 8 and 4. So now I can immediately write down all the things they're asking here. Okay, so U mean and U max are actually pretty easy to do. U mean and U max are just a normalized vector of the gradient vector, right? So U max is equal to gradient of f divided by length of the gradient, so it is equal to 8, 4 divided by square root of 8 squared plus 4 squared. I think I'm getting a
90. 80.
So
80. Square 80.
it's basically 2, 1. So it's just 2 square root of 5 and 1 square root of 5. You can do your own computation, right? It's just a matter of, I have to make sure this is in the same direction, which means as long as the ratio between these two components is 2, it's definitely going to be the same direction. And I want to make sure it is normalized. You can follow the simplification right here. Just simplify the number, compute whatever you have.
I just wondered if you could repeat how you found the gradient again.
Oh, the gradient, I'm sorry, yeah. The gradient is really defined as the two components as the partial derivatives. Yes, I really should write down this more often. Right? By definition, the gradient is a vector with two components. X component is a very symmetric way, actually. The X component is the partial derivative in X. The Y component is partial derivative in Y. Yeah, that's what I did here. So gradient is very symmetric. And then U mean is going to be the minus direction. So it's going to be minus 2 divided by square root of 5, minus 1 divided by square root of 5. I'm computing these two in the very beginning. Therefore, if I want to write down the maximum and the minimum value of my directional derivative, I can write down them explicitly. So the maximum is definitely du in the maximum. So this is exactly where I will achieve the maximum direction. This is exactly where I will achieve the maximum rate. So it is equal to the length of the direction. Okay? I'm sorry, the length of the gradient vector. So this is going to be square root of 8 squared plus 4 squared. You're getting 4 square root of 5, right? And d minimum is equal to minus length of the vector, which is equal to minus 4 square root of 5. Okay, so the steepest ascent rate is going to be 4 square root of 5, and the steepest descending rate will be minus 4 square root of 5. And then in the end, I can look through my work, and everything is making sense. Vectors, I have two components. Vectors in R2, I have two components. Directional derivative, I'm supposed to have a number. Directional derivative, I have to have a number. Okay? Questions? Okay. If there is no question, I'm going to propose even more interesting relation between my gradient and another object when we learn the graph of functions. So do you still remember this contour map we drew in the very beginning, consisting of level curves, right? So maybe I'll give you one example for that. It's equal to 9 divided by x squared divided by 25 minus y squared divided by 4. Okay, so let's look at this example. Quick test. What is this surface? If z is equal to 9 divided by x divided by 24, y divided by 4, this defines elliptic paraboloid, right? Opening in the z direction towards negative direction, right? So basically, it will be looking like this.
That's what I
Okay.
Shit.
This is what we have. The vertex is going to be 9 sitting on the z-axis, and it is opening downwards because both of them are negative. Okay. We can actually draw the level curves without even drawing the three-dimensional surface. So f x y is equal to 9. You're getting a. If I pick my level to be x equals z equals 9, I'm getting 9 minus x squared minus y squared divided by something is equal to 9. So it's equal to 9. So I'm getting exactly a point,
0, 0.
right? 0, 0. So 9, 9, you got a square equal to 0. The only possibility is x 0, y 0. So the level curve, when the level is at 9, it is exactly a point. Then we can choose f x y, say, is equal to. I have to make sure this level is within the range. Sounds foreign to you, shouldn't? Remember when we first discussed the graph of a function, we look at the domain and the range, and when we want to draw a level curve, so we have to make sure the levels are within the range. For instance, I can choose my level to be equal to 10. I'm not going to get any point because it is going to be out of the range here. All right? So this is 9 minus something square, something square. This guy is definitely less than equal to 9. Right? So I can choose, say, it is equal to 6, or so it's going to be 9 minus x squared divided by 25 minus y squared divided by 4 is equal to 6. This is a very quick user's manual for drawing the level curves. Okay, so this guy is going to give me x squared divided by 25 minus y squared divided by 6 is equal to 3. And then I can divide 3 on both sides, so 6 minus 3 is equal to 1. This is the level curve on xy plane with the level equal to 6. And this equation defines
Ellipse.
an ellipse, right? It is not exactly a circle yet, but it's an ellipse with x-axis 5 square root of 3 and y-axis 3 square root of 2. So basically it's x and y is going to be ellipsing. It's not very precise, but it has to be an ellipse looking like in this shape. And then I can choose different levels is equal to 3 or so ever. When I decrease my level, and then this ellipse will become bigger and bigger, right? So basically, I will have a family of level curves. They're all ellipses. So the very middle, the origin corresponds to the level 9. And then when the level is decreasing, because of this negative sign here, this ellipse is going bigger and bigger. So you combine all these things together, you're getting a contour map. This is what we did. Hopefully you still remember this, okay? So this is the level k equals 9. This is the level, for instance, k equals 6, and so on. So when the levels are decreasing, you're getting a family of level curves. Okay. Now I'm going to propose my interesting question here. So if I'm looking at this curve, okay, if I'm looking at this curve, particularly, I can arbitrarily pick a point right here. In fact, any point sitting on this curve is sitting on the xy plane, all right? So if I'm looking at this curve, all the points sitting on this curve have one common thing happening,
Z equals 0.
which is z equals 6, all right? So a point is sitting on a level curve if and only if the z value is the same, right? All the points sitting on the middle, which is exactly just 1, corresponds to the function value equals 9. And this curve corresponds to all the points where the function value is equal to 6. In other words, if I'm moving around on this level curve, my function value do not change at all. Are with me? I'm on the same height. If you're still remembering the graph of a mountain, you cut it into different levels, and then you project all the curves back onto the xy plane. These curves are exactly talking about the points where the level are the same. which means they're on the same height. All right? Now with me. All the points here, they have the same function value. In other words, if I'm moving along the level curve, the rate of change is equal to
0.
0. All right? The rate of change is equal to 0. Looking at this particular example, what do you tell?
No, data equals 9.
You're just randomly seeing things,
Data
right?
equals.
I want to relate the level curve with the gradient vector, right? You can only achieve rate of change to be exactly 0 if the direction is within the orthogonal direction of the gradient vector. And I know if I'm moving along the level curve, I will get a rate of change of 0, which means if I'm moving along the level curve, I am moving in the orthogonal direction of the gradient vector. In other words, the gradient vectors are all orthogonal to level curves. So at every point on this level curve, the gradient is exactly orthogonal, okay? So this is a very interesting fact. So any point, the gradient vector is orthogonal to the level curve. This is because if you move on the level, the same height, the rate of change is equal to 0. So the gradient has to be exactly in the orthogonal direction, okay? Okay, so furthermore, I can even tell more things here. Remember, you will be able to tell a lot of information from looking at the contour map. You don't have to go three-dimensional. This is the old way. Maybe 100 years ago, all the military minds are looking at this map instead of the 3D computer-generated things. So if I'm looking at this map, not only I know the gradient direction is the orthogonal direction with the level curve, I can also tell U max and U min. Because I only know the gradient vector should be orthogonal, but there are two directions to choose from. Okay? So this is k equals 9. This is k equals 6. If I'm going into the maximum direction, my function value is supposed to increase. So this is supposed to be u min. And the opposite direction is going to be u max. Okay? So the level curves are very closely related to gradient in the following way. At every point, the two directions where you achieve the maximum rate of change or minimum change will be all orthogonal to this level curve. And the U minimum will be towards the direction where the levels are decreasing. And also U maximum will be going towards the directions where the levels are increasing. Okay? So this is exactly what we have, because when I decrease the level, my circle or my ellipse are getting bigger and bigger. So from inside going outside, the levels are decreasing. So this is exactly the direction of the U minimum. And going inside, I'm going to increase the levels. So that's the U max happen. Okay? Questions? Try to convince yourself this is indeed happening. Okay? The other thing I want to talk about, which is lastly more involved. I want you to be convinced this is not from mathematics alone. It is also a very practical reason if you want to design your strategy. Okay? So I'm picking 2 points. One point on one level curve, the other point is coming from a different level curve. Okay? If I go from one level curve to the other level curve, for instance, if I go from k equals 6 to k equals 3, my change of z variable in the z is always equal to 3, right? As long as I jump from one level curve to the other level curve. Does not matter which their 2 points are, right? I can jump from here to there, here to there, here to whatever, as long as I can jump from one level to the other level. Change of z is always the same. But the rate of change will be different. If I can achieve my change in z of 3 in the shortest distance, my rate of change will be
Greatest.
All right? And I'm saying if I go from one level curve to the other level curve, if I go in the orthogonal direction, the distance is the shortest. Therefore, it will achieve the maximum or the greatest, minimum or maximum, but it will achieve the greatest possible rate of change. Imagine if I go orthogonally from one level curve to the other curve, I will achieve this rate of change by 3 within this distance. But if I go in other directions, this distance will definitely be greater than the other one. Okay? So from one level curve to the other level curve, you want to achieve the greatest rate of change. The best way to do that is to go orthogonally. Okay? That's the other way of understanding why this is indeed the case. Okay? So this is a change in the xy. Okay? So this one will be the shortest in the orthogonal direction. Okay? So now, even though we're talking about calculus and derivatives and directional derivatives, now if you look at the contour map, you can easily see a lot of information from that. Right? If you have a lot of level curves cramming together, this is where the directional derivatives are large, where the change of slope is pretty large. That's where the steepest ascending or descending is happening. If the level curves are a lot of space between the level curves, that's where the slope is small and the rate of change is also small. Okay, but we are talking about a calculus, so we should be able to do things. So I want to quickly verify one thing. So fxy is equal to 21 minus x squared divided by 4 minus y squared divided by 25. So I'm at a point 2 square root of 3, 10. Okay? And this point is on the level curve fxy is equal to 14. You can verify yourself. Okay? So if I plug in these two values in there, I'm getting the function value is equal to 14. So this point sits on a level curve with level 14. So I want to compute the following things. I want to compute the gradient. And also I want to compute the tangent line of the level curve, or the slope of the tangent line. Slope of the tangent line. To fxy is equal to 14. And then I want to